Okay, so we're going to get started. So today we're going to be learning about triangles, and specifically we're going to be learning about triangle area, perimeter, and we're going to learn about how to classify triangles. We're going to learn about what the Pythagorean Theorem is and how to use them to find the lengths of the sides of a triangle. And we're going to learn about similarity and congruence. Okay, sorry.
All right, so in order to find the area of a triangle, we multiply the base, the height, and then we multiply 1/2. And in order to find the perimeter, we just sum up the lengths of all the sides of the triangle. So we have an example below. So the triangle shown has a base length of 14 and a height of 6. So using these figures, can somebody tell us what the area is? Yeah, okay. So I think I have like answers in chat.
Yeah, you could just type your answer in the chat.
Yeah, so Dip got it. Yeah, so basically it's 42, and how we get that is, well, we know the base and the height since they're given in the question. So the base is 14 and the height is 6, and then we multiply that by 1/2. So then we would get 42.
Okay, so here's another example. The triangle shown below has side lengths of 14, 12, and 8. What is this triangle's perimeter? And you can just type your answer in the chat.
All right, so I think most of the people are getting it right. So
yeah, so the answer is 34 because you just add up the lengths of the triangle. So that's 12 plus 14 plus 8, which is 32. Okay.
So now we're going to, oh, it's my bad.
Okay, so for this next slide, we're going to learn about how to classify triangles in 2 different ways. And the first way you can classify triangles is using the lengths of the degree measures of their angles. And there are 3 types of triangles. The first type are called right triangles. Right triangles have one 90-degree angle, and the other angles can be any value, just as long as they aren't 0. The second type of triangle is called an obtuse triangle. These triangles have one angle that is greater than 90 degrees. And finally, the third type of triangle is an acute triangle. And acute triangles have all 3 angles as less than 90 degrees. And we're going to pause so you can write this down.
Also, so I think most of you guys know this, but the sum of the angles in every single triangle is always 180 degrees.
Okay, we're going to move on.
Yeah, there is an equilateral triangle, but that would just be...
that's for another thing. Just hold up on that.
But an equilateral triangle would just be classified as an acute triangle, right? Since all 3 angles would be less than 90 degrees.
Okay, so we're going to move on. Sai, you can take this.
All right, yeah. So now we're going to classify these triangles further. So we use side lengths to further classify these triangles. And there's 3 different triangles we can classify using the side lengths. So we can classify triangles using equilateral, isosceles, and scalene. So an equilateral triangle has 3 equal sides, and all the angles in an equilateral triangle are the same. So that would be 60 degrees. The next kind of triangle is an isosceles triangle. An isosceles triangle has 2 equal sides, and that means that it also has two equal angles. The final type of triangle is a scalene triangle. A scalene triangle has three sides like all other triangles, but all three of these sides have different lengths, meaning all three of the angles also have different degree measures.
And we can pause to let you write this down. And also, a note about the symbols on these triangles. Normally, triangles are just made of 3 lines, but in these diagrams, we can put tick marks on the sides to show which sides are equal. So for example, in an equilateral triangle, all 3 of these sides are going to have 1 tick mark, which means that all of the sides that have 1 tick mark are going to be equal. In this equilateral triangle, we can see that 2 of the sides have 1 tick mark, and the third side has 2 tick marks. What this means is that the sides that have 1 tick mark are equal, and then this side with the 2 tick marks is just by itself. And finally, you can see that in the scalene triangle, there's a side with 1 tick mark, a side with 2 tick marks, and a side with 3 tick marks. That just means that all the sides are of different lengths. You can also use the same thing with these curves that represent angles. These angles can either be like have 2 curves on them, or the angles can also have tick marks on them to show which ones are equal. And finally, right angles will always have this square angle symbol. Okay, we're going to move on now. So, yeah. First, we're going to look at an example. So, what type of triangle is this? And you can just type your answer in the chat, and there may be more than one answer.
All right, so it seems like everybody got the answer right. It's scalene, and it's also somebody also said obtuse. So yeah, so since one of the angles, which is the topmost angle, is greater than 90 degrees, we know that it's an obtuse angle, and we also know that the side lengths of the triangle are all different lengths, so that would make it a scalene as well.
Okay, for this second example. What type of triangle is this? And this image is not drawn to scale, and there may be more than one answer also.
Yeah, so it looks like a lot of you guys are getting the right answer. So everybody said right. I mean, most people said right. So we know that it's a right angle triangle based off the square, which indicates a 90-degree angle. And we also know that it's an isosceles triangle based off of the tick marks. So since 2 sides have the same 1 tick, that basically indicates that both of these sides are of equal lengths. And we know that triangles that have 2 sides of equal lengths are isosceles triangles. So the correct answer is right/isosceles.
Also, this picture, you may have noticed that this picture, although the tick marks are saying that these 2 sides are equal lengths, the picture makes it seem like that they kind of aren't of equal lengths, because you can, if you put these sides right next to each other, you'd actually see that this bottom side is slightly longer than this vertical side. But that doesn't matter. The question says that an image is not drawn to scale. So what this means is that you have to rely on the tick marks to tell you which sides are equal. So even though this side and this side don't look like they're equal, the tick marks tell you they are. Okay, for this third example, what type of triangle is this? And as a hint, this is kind of a trick question.
All right, so a lot of people are saying equilateral, acute, and scalene, but the correct answer to this question is that we don't really know. I mean, I'm assuming that's the correct answer since I haven't really
We don't,
exactly.
because the question, it doesn't say that the image is to scale. And what
And
to
it doesn't give us
scale,
any.
yeah, what to scale means is that you can just look at the image and tell what it is, but it doesn't say that it is to scale, which means that although it kind of looks like it's equilateral, you don't really know for sure. And although it looks like it's acute, like you can't really say for sure because there's no angle marks that tell you that which sides are equal or angles are equal. There are no tick marks telling you which sides are equal. So if the question says, like directly says that the image is to scale, then you can just eyeball it and say, oh, this is equilateral. But this question doesn't say that it is to scale, so you can't really say anything.
Okay,
So
so somebody says, but isn't it obvious that it's acute? Well, we
yeah, I
actually
guess you
don't
could.
really know. So an acute angle has all three angles that are 60 degrees, but one of the angles could be 59.9 degrees, and that would immediately not make it acute. So if one angle was
No.
59.9 degrees,
Acute is just less than 90 degrees.
My bad. I thought he said equilateral. Okay, that's my fault. I was kind of like having a brain piece. But yeah. So most importantly, most of the things that you can assume about a picture comes from the symbols. So if the triangle had tick marks on all the sides, then we could assume, well, we would know that it would be an equilateral triangle and an acute triangle based off of the symbols that indicate. So, but since this picture doesn't have any symbols and the question doesn't tell us anything about it, we can safely say that there isn't enough information to answer this question.
So the lesson from this question is that in math counts and just any like math competition in general, don't assume that the diagrams are to scale, because sometimes in math counts they will provide you questions with diagrams, but even if a triangle looks a certain way, you can't assume that it really is. And that can also apply to the when you draw your own diagrams. Sometimes in math counts they give you information about a shape and you have to draw it yourself. Sometimes if you're not good at drawing, you can't even trust your own drawing. Well, on a math counts test, there's never going to be a question where they're going to ask you something like a property about a shape without telling you about what it is. Mostly in math counts, they'll just ask you to solve for like the length of a side. They'll ask you to solve for a number. So in that case, you don't want to assume something about an image, which could be false. But like this type of question, that's like a trick question, this won't come up in math counts. This is just to demonstrate that you shouldn't always trust a diagram. Okay. So now we're going to learn about what the Pythagorean theorem is. And the Pythagorean theorem is a rule about the lengths of a right triangle. And this is a very useful and helpful rule. And it's actually pretty simple. It is just a squared plus b squared equals c squared, where a is the length of a leg of a right triangle, and b is the length of the other leg of a right triangle, and c is the length of the longest leg of the right triangle, which is also called a hypotenuse.
And the way we can identify the hypotenuse is the hypotenuse would always be the side that's opposite of the right angle. So we know that the right angle is between the side lengths of A and B. So, and then the side that's opposite of that would be C. So in every single right triangle, the hypotenuse is always opposite of the right angle. So that's how we identify that. And also using the Pythagorean theorem, C is always the hypotenuse, and A and B are always the legs. So that's super important to remember. You can't really interchange these.
Yeah, and just to clarify, the legs are the sides of the triangle, which are kind of like connected to make a right angle. So you can see here that side A and side B, when put together, like they're the ones that are right next to the right angle. And side C is the one that's opposite the right angle.
Yeah,
And
so
this,
basically the legs are just everything that the hypotenuse isn't. So like once you identify the hypotenuse, you automatically know what the legs are.
and A and B can be equal. And you can also switch the places of A and B. So B could take place A and A could take place B. And they could be equal. They could.
Yeah, but that would only be isosceles right triangles, which we're probably not gonna go
Yeah,
into.
we're not going to talk about isosceles right triangles yet. So yeah, we're going to pause for a second so you can write this down. This is very, very, very important. So
All right, we're probably gonna get it. Okay, Okay, so in order to find a missing leg, you still use Pythagorean theorem. You just rearrange the variables. We're probably just gonna get into that later, so I'm probably just gonna explain that once we get into like
There will
actual
be
examples.
there'll be a couple of examples about finding a missing leg. And
Yeah,
yeah, like Sai said, you would just rearrange the equation. So if you knew what C was and you knew what B was, but you didn't know what A was, what you could do is you could just plug in the value for C and plug in the value for B, and then you can solve for A.
that might sound a little confusing now, but I think it'll make a little more sense once we get into like examples.
Yeah. Okay, we're going to move on to an example. So, example 4. If a right triangle's hypotenuse has a length of 5 units and a leg has length of 3 units, what's the length of the other leg? And for this question, you should just plug in the values of 5 and 3. You should use the value of 5 for C and the value of 3 for A or B. It doesn't really matter. And then you can solve for the remaining one.
And we have a quick question.
Yep.
Are we going to get into Pythagorean triples?
No, but we can touch on that if you'd like.
All right, we'll probably do that like at the end because I don't think it's really like
it's not necessary.
It's important, but like yeah, I think people are getting 4, so that's the correct answer. So so we know that C is 5 because it clearly says that the hypotenuse has a length of 5, and we know that the hypotenuse is C. So using the equation, we can say we know that one of the legs is also 3. So we're just gonna make an equation: 3 squared plus x squared is equal to 5 squared. And once we simplify that, we get 9 squared plus x squared is equal to 25, which we can simplify to x squared is equal to 16, and x would be 4. So 4 is the correct answer. And like to solve this problem, you could also use like a Pythagorean triple, but like we probably won't get into that.
If it's irrational, well, we're not going to get too much into that. If it's irrational, you would have to use a square root. And yeah, you would just do that. But you would have to simplify the square root too. Okay, we're going to go to another example. The 2 legs of a right triangle have lengths 6 and 8. What's the length of the triangle's hypotenuse? This time, try to identify which values are A, B, and C, and try to solve it.
All right, so it looks like most of you guys, got the correct answer. So the answer is 10. And so we know that in this, we know that the legs of the right triangle are 6 and 8. So we know that A is 6 and B is 8, or you could switch those, but because it really doesn't matter. So we know that 6 squared plus 8 squared would be C squared or X squared. And simplified, that would just be 100 is equal to X squared. So we know that in that case, X would be 10. All right, I think we can move on.
Okay.
But does anybody have any questions so far about anything at all? You can just unmute yourself, or I guess just type in chat, or just send something privately to Amy or me.
Can we go over one more example problem?
Yeah, I don't. Amy, is there another example?
We can improvise a problem. So, hold on. Whoops. Okay, this time let's say that the lengths of the legs, instead of them being 6 and 8, let's make them be 5 and 12. So then solve for the triangle's hypotenuse. So you can type that in the chat. 5 and 12 are the lengths of the legs.
All right, so I think, never mind, we only have one answer, sorry.
Yeah, it would be radical 169, but see if you can simplify that. because we're not going to get into like square roots or anything. So yeah.
13. So I think people are getting the right answer. So we know that the legs means A and B would be 6 and 8. So 6
It's not
squared
6 and 8, it's
oh,
5 and
sorry,
12.
yeah, I kind of forgot. So 5 and 12. So that'd be 5 squared plus 12 squared. And 5 squared is 25. 12 squared is 144. 25 plus 144 is 169. So we basically, the x squared is equal to 169, meaning x is equal to the square root of 169, which is 13. So the answer is 13.
Yeah, we don't have a slide for this because we just wanted to
We had to
provide another
improvise.
example. Yeah.
So does everybody get Pythagorean theorem and how we can kind of change up the equation to find the legs instead of the hypotenuse?
Yeah, but I have an easier way to do it.
Can would you like to share with us the easier way?
Sure, I don't know if it works for every single problem, but so far it works for all the problems. So you add the two things together, then you minus that by 4.
I don't wait,
That's a good strategy, but unfortunately, it's not going to work for all of them. So, for example,
Amy, can you go back to the other problems really quickly?
okay, that's a good strategy, but it's not going to work for all of them.
Oh, he's actually right.
Yeah.
All right. Okay.
That's smart, but that's not going to work for everything. So let's look at another example then. Let's look at let's go forward. Wait. So for now let's say if A is, okay, you may not get this, but if A is 5 and if B is 24, what is the value of C?
Wouldn't you use? Wait. So wait. What is A?
7 and B is
Seven,
24.
Okay, so it's 7, 24.
Yeah. In that case, what would be the value of C?
Yeah, she's right. That's. You could have also just done 10, 24, 26. 25. All right, so it looks like people are getting the right answer. 25 is the correct.
Yeah, radical 625 is the right answer.
Could be simplified as 25.
Yeah, square root of 625 is 25.
So like it's important to keep in mind, I think that's really important to learn your radicals because in math counts, you always have to include the answer in simplest radical form.
Yeah.
Well,
Yeah, Shreyam, you would have to simplify it. They will accept radicals in certain problems, but most of the time, if they don't say anything, they won't be accepting radicals.
In Pythagorean theorem problems, they're never going to accept, like if the answer is 7 and you put root 49, then they would mark that as incorrect.
Okay, so I think we
got this for the most part. Does anybody have any questions, or do you want? Wait, what was his strategy? Okay, his strategy was that you would add up the legs and then subtract 4 to get the hypotenuse. That strategy does not work for all problems, and we highly discourage you to use that.
It just happens that for all the problems we've had so far that turned out to work, but that won't work for our problems. Okay, so we're gonna move on to another topic now. Okay, so now we're going to discuss similarity and congruence. So similarity is, or in other words, when two shapes are similar, it means that they have the same angles. Well, their side lengths don't have to be different, but they have the same angles. And basically, if two triangles are similar, that would mean that one of them is like scaled up. So this picture here. This small triangle is basically just a smaller version of the bigger one, and bigger one's a bigger version of the smaller one. And if you measure the angles of this triangle, you would find that all the corresponding angles would be the same. In other words, this angle would be the same as this angle, and this angle would be the same as this angle, and so on. And that's also the definition of similarity.
The ratio the lengths of the sides are proportional, so that means like they would be in the same ratio. So I don't really have like a mouse pointer to like show you
So
guys.
yeah, like this side, the
If that was
ratio of
5,
this side to this side would be the same as the ratio of this side to this side.
this side. So if that was 5, if the leftmost side was 5, and then the other leftmost side of the other triangle was 10, and then the other side was 4, that means the corresponding side to the larger triangle would be 8, since the ratio is 1 to 2.
Okay. And now congruence is actually a little bit, it's simpler than similarity. Congruence just means that two shapes are exactly the same. Just like maybe they're in a different position or they're rotated a little bit. But other than that, they're exactly the same. So these triangles, they're congruent because they have the same angle measures and the same side lengths. They're just in different positions. And if I rotated this triangle, these two triangles would still be congruent because they're technically still the same thing. Okay, so yeah, in congruent triangles, the side lengths are the same, the angle lengths are the same, the area and perimeters of the triangles are also the same. So these things, basically everything about the two congruent triangles would be the same, except for like their maybe position. So for example, triangle ABC has side lengths of 4, 9, and 11. Triangle XYZ is congruent to triangle ABC. What is the sum of the side lengths of triangle XYZ? Or in other words, the perimeter?
Yeah, so it looks like 2 people got the right answer. I mean, I actually think, yeah. So the right answer is 24, since XYZ is congruent to ABC, meaning all the side lengths and all the angles are the same. These two triangles are literally the exact same. And basically, when it's asking the sum, it would just be the perimeter of triangle ABC, which is 4 plus 9 plus 11, which is 24. Also, I noticed that only 2 people put the right answer in chat, and this was a relatively easy question, so I would encourage more active participation.
And yeah, if you'd like to write this first part down, the sides, angles, areas, and perimeters of two congruent triangles are always the same. We can pause for a second to let you do that.
Also, if you aren't sure in the answer to a problem, I still encourage you to just put an answer or just guess. Because it kind of lets me know that you guys are participating. And it's kind of important since triangles are probably one of the most important things in math counts or just any other math competition in general. Actually, just math in general, really.
Okay, now we're going to move on. Okay, so in similar triangles, the corresponding angles of the triangles are the same. In other words, these two triangles here, if they're similar, then that would mean this angle is equal to this angle, and this angle would be equal to this angle, and this angle would be equal to this angle. Also, the sides and perimeters are proportional to the scale factor. And what the scale factor means is that it's basically what you multiply to go from one triangle to the other triangle, which I'll explain more of what the scale factor is in a second.
So the only difference between similar triangles and congruent triangles is that similar triangles just have different side lengths.
Yeah.
That's the only difference. And that too, these side lengths are proportional, meaning that, like Amy said, they're either scaled up or scaled down. That means the perimeter will always follow a proportion.
Yeah, and we'll show that more in a second. Also, the areas of both triangles are proportional to the square of the scale factor. So, for example, and the scale factor is the number you multiply to get from one triangle to the other. So, for example, if this triangle here has side lengths of 2, 3, and 4, and this triangle here has side lengths of 4, 6, and 8, you can notice that the side lengths of this bigger triangle are twice the side lengths are of the first triangle. They're doubled. So this would mean that the scale factor from triangle ABC to triangle XYZ would be 2, because the side lengths of the XYZ are twice the side lengths of triangle ABC. This would also mean that the perimeter of triangle XYZ would be 2 times the perimeter of triangle ABC, again, with the scale factor. And the area of triangle XYZ would be 4 times the area of triangle ABC, because we've determined that the scale factor is 2. So, and the area of both triangles are proportional to the square of the scale factor. So since the scale factor squared is 4, this would mean that triangle ABC has an area that's 4 times greater than triangle ABC. And we're going to show more examples for this in the following slides. And we're going to pause to let you write this top part down. Okay, now we're going to go look at an example. Oh, okay, we have a quick thing about notation first. Sai, you can do this slide.
Yeah. So to say that two triangles are similar, we can write the triangle symbol, which is just a triangle, and then a kind of a curvy symbol. I don't know exactly what that's called. Do you know what it's called, Amy?
No, I don't know what it's called. We can just call it the curve.
Let's just call it the curvy, all right? So the curve, right, basically indicates that two triangles are similar. So we have triangle ABC and triangle XYZ. To say that both of these triangles are similar, we use the curve. Since triangle ABC and triangle XYZ are similar, we know that AB corresponds to XY, BC corresponds to YZ, and AC corresponds to the side YZ. And we also know that all of the angles of both of these triangles are the exact same. Well, the corresponding angle.
Also note that the order that you write these letters matters. So if instead of writing triangle ABC is similar to triangle XYZ, if instead of that you switch the positions of letter A and letter C, that would also change which sides are corresponding to each other. So
that would, yeah, that's really important.
Yeah.
If we changed A and C, then we would basically be saying side CB is corresponding to side XY, which is simply not true.
Yeah, and Shreya pointed out something. Side AC is supposed to correspond with XZ, not YZ.
XZ,
That's
yeah,
a typo.
That must have been, yeah.
Sorry. Also.
All right, to say that, yeah. Okay,
yeah, Sai, you can do that.
All right, to say that two triangles are congruent, we kind of use the same curvy symbol, but then we also put the equal symbol below that. So it's kind of just an equal symbol with the curvy symbol on top. And that basically lets us know that triangle ABC is congruent to triangle XYZ, or two triangles are congruent. And that would mean, well, we wouldn't really say correspond. We would just say that side AB is equal to side XY, side BC is equal to side YZ, and side AC is equal to side XZ. I think the last one's also a typo, Z. All right, so yeah, and the letter matters so much, and you'll never really like encounter something in math counts where like the order matters in a question, because I don't really know if I've encountered that. But like when you're like working out a problem, it's super important, because you could easily get confused between which sides are equal and which sides are like corresponding and stuff like that.
Okay, so now we're going to move on to a couple of examples. Okay, so in this question, triangle ABC and triangle XYZ are similar. Triangle ABC has side AB equals 6, and triangle XYZ has side XY is 24. If side BC equals 2, what is the length of side YZ? And if this question has too many words, you can just draw a picture. You can draw two triangles and label the points A, B, and C, and X, Y, and Z. And then you can look at which sides are corresponding to each other. And then you can solve for the lengths.
Amy, do you want to call on someone and ask how they got the solution?
Okay.
All right.
You can call on someone.
All right. So I'm going to call on one of you who answered, and I'm going to ask how you got the solution. All right. Looks like 2 people answered. All right. Sanjay, how did you get the answer? How did you get 8?
It's because like it said it was similar, so like x times 4. No, I meant 6 times 4 equals to 24. So I did 2 times 4 equals to 8.
Okay, that's true. But then, but how do we know that side BC is correspondent to side YZ? It's okay if you're unable to answer. Like, yeah, you did a great job. Thank you for answering. So we know that side BC is correspondent to side YZ based off the order. So we said before the order matters a lot, and we know that BC is in the same order as YZ since BC comes in the same in the last 2 parts, and YZ also comes in the last 2 parts. So we know that BC is corresponding to YZ. So that's how we know it's 8 as well.
A second way you can do this, like this first way is basically the easiest way, which Sanjay told us about. If you want, there is another way which you can set up a proportion and solve it. You can see here that the ratio of AB to XY should equal the ratio of BC to YZ because these sides are corresponding. And then you can substitute and solve. This one's a little more complicated though, and it may be confusing. So just stick with the way that Sanjay told us to do. Okay, the second example. If the 2 triangles in the image are similar, find the value of x.
Well, even if we weren't like really given the question, and if the question was just find the value of x, you guys should immediately know that the triangles are similar based off of the markings.
Yeah, because you can see this angle, this angle is the same as this angle because there's a tick mark telling us that they're equal.
Ring. And 1 ring, and then the other one has 2 rings, and the bottom one also has 2 rings. And if we know that 2 angles of both triangles are equal, then we know that the third angle has to be the same. And that's basically kind of like a theorem, but we're not gonna get into all of that.
Just know
theorems. Yeah,
just know that if 2 triangles or 2 angles in a triangle are similar, and if
there's 2 similar triangles and if there's 2 triangles and both of these triangles have 2 angles that are the same, then they're both similar triangles or congruent. But yeah,
at least you just know they're similar. You don't know if they're congruent.
Yeah. I mean, actually, congruent triangles would also be similar too. They would just have
technically.
Yeah. I mean, all these things have to do with math counts in some way. And like by learning the things that you might not necessarily encounter in math counts, you still get a general idea of the entire field, which actually helps in math counts.
The things we're not getting into, they're just, I mean, if you know like the general gist of it, then that's fine. I'm pretty sure like most people in the room will actually, virtual room, will probably already know like what we're not getting into. It's just you don't know the specific name and it's not a formality. So yeah.
Wait, sorry, did anyone answer? All right.
Yeah,
so it looks like some people answered. So it looks like a couple people answered. So the correct answer is 15. So we know that both of these triangles are similar. One was stated in the problem, and we also know based off the angle markings, but let's just say that we saw that they were similar in the problem. So now that we know both of these angles are similar, we just need to look at the corresponding sides. So we know that the bottom sides are both corresponding since they're both like the widest of the triangles. So that has a ratio of 1 to 3, right? Because 9/27 is 1/3. So we can set up a proportion. 5/x is equal to 1 to 3. So that means, and then once we solve that, we just get x is equal to 15. Or we could just multiply 5 by 3 and just get 15.
Because to get from the smaller triangle to the big triangle, there's a common scale factor. In other words, to get from this side to this side, you have to multiply by a number. And this number is 3 because 9 times 3 is 27. This also means that, in other words, this side is 3 times bigger than this side. So this would mean that x is 3 times bigger than 5. So that would mean x is 15.
I have a question.
Yep.
So let's say I understand what this is, but let's say instead of having 27 there, if they have like something that's not a multiple of 9.
In that case, if it weren't a multiple of 9, there would still be a scale factor, but the scale factor would have to be a fraction. And then that would also mean that if you multiply that by, it would still be the same, except you would just do this number divided by 9 to get the scale factor. And then you multiply that number by 5 to get x, which may be a fraction.
Okay, so we cannot add and stuff.
Say that again.
So we can't add, like let's say after not, let's say instead 27 is 10, and then that's 1 away from 9, so we can't add. We have to only multiply.
Yeah, you can't add. You have to multiply.
I mean, for any similarity problem, we would always multiply.
Yeah,
you should never add similarity.
Adding usually, it's sort of like if you have like a square and another square is 4 times bigger. If you add, it doesn't like keep the size. It doesn't keep them proportional. It's kind of hard to explain, but you have to multiply. You can't really add.
So you can't use Pythagorean theorem on this shit. I don't really know what
shape. No, you can't.
Shape.
You
Sorry,
can't. Because
you
this
can use Pythagorean theorem on the shape because it's not a right triangle.
I mean, if it were a right triangle, you could, but it doesn't say it is a right triangle, so we can't use it. Okay, we're going to move to another example. For this example 8, triangle X has an area of 7, and triangle Y is similar to triangle X. If the scale factor between them is 3, what is the area of triangle Y? And when I say the scale factor between them is 3, it means that to get from triangle X to triangle Y, the scale factor would be 3.
Also, I don't think this problem clarifies which one is the bigger triangle.
Yeah, I just clarified it. It's the scale factor is from triangle X to triangle
Y. So you would multiply by, so Y is the bigger triangle.
Yeah, Y is the bigger triangle. We've got some conflicting answers in the chat.
All right, so 2 people said that the answer was
Hold on, sorry. Let's let the other people type.
All right, yeah, my bad. Sorry. Yeah, okay, cool. Yeah, more people are putting in their answers.
Yeah. So actually, let's let Shriyam, tell us what are your thoughts on how to solve this problem? So what did you do?
Basically, So before we kind of, yeah. I thought you said Sai. Oh, who are you talking to?
Shriyam.
Oh.
Yeah. How did you solve this problem?
So you said the area would equal the scale factor squared. So 3 times 3 is 9. So then I multiplied 7 by 9 and got 63.
Okay. That's right. That's exactly how you're...
Yeah. It looks like the other people, you forgot
just
that
multiplied 3. Yeah. They forgot that the scale factor, they just multiply the scale factor in the triangle, but they forgot you have to square the scale factor and then multiply by the area instead of just multiplying the scale factor.
Yeah, so for this problem, it's asking about the area. So you would have to scale or square the scale factor. So yeah, the area is going to be 9. The area of triangle Y is going to be 9 times the area of triangle X. So you would have to do 7 times 9, which is 63. So you have to remember this. If it's asking about the area, then it has to be the scale factor squared. So we've told you that the scale factor is 3, but you have to square it before using it to find the area.
Are we gonna move on? Or they're just writing this down?
Yeah, just keep that in mind. Does anyone have any questions on why this is squared?
Or just any questions in general at all about anything that we've covered today? Or just anything? Okay, but do we have class next week? Is it next week winter break?
I can check the schedule.
We have class every day until the 25th of December, and then we don't have class then or the 1st of January.
All right, so basically we have class next week, but not the week after that. So we have class next week, basically.
Okay, and I'm gonna explain how we know it's squared. So if you don't have a piece of paper, you may want to get it out because I'm gonna be asking you to draw something. So, okay, so first on your piece of paper, or if you don't have a piece of paper, you can just visualize it. First, to draw a square. Okay, draw a square. Now draw four squares that draw four squares to well, not four squares. Draw one square that has a side length of 1 unit, and then draw another square that has a side length of 2 units. So the second square should have a side length that's twice the side length of the first one.
Amy, can you do that on Jamboard?
Oh yeah, that's a good idea. Hold on a
Jamboard,
second.
so then everybody can see.
Yeah, okay. Let's add a slide.
Wait, so you have to draw one normal square and then
Yeah.
one square that's 1 unit bigger, and then another square that's another unit.
Amy will
bigger.
just, yeah. I
Yeah,
mean,
we
I
can
think you
just
get
draw
the general
here.
idea, but I guess Amy's just gonna draw it on a. Wait, I'm pretty sure this is a shape tool, Amy.
I know, I'm looking for it where.
It's right there. It's a
Oh,
circle.
shoot, okay. So first we're gonna draw a square. Oops. Okay, this is a square. And now we're gonna draw a square whose side length is double this squared. So, in other words, in order to draw a square with a side length that's double this square, we have to use 4 of the other squares. You see? And now we're gonna we can also draw a square with side length that is 9 times, or side length that is 3 times. So now you see, here is a square with side length 1. This is a square with side length 2. And this is a square with side length 3. But the area of this square is 1. And the area of this square is 4. And the area of this square is 9. So even though the side lengths are directly proportional, the areas have to be squared, you see? So for triangles, this is the same. If you go from a triangle with side length 1 to a triangle with side length 3, although the length of the sides and the perimeter would just be multiplied by 3, the area would have to be multiplied by 9 because it's proportional to the square of the scale factor.
Yeah. Basically, the side lengths are arithmetic and the areas are geometric. If we kind of made it a sequence, so that if the side lengths are 1, 2, and 3, and the areas are 1, 4, and 9. So if we made a sequence of consecutive areas of squares, that sequence would be geometric. And then if we just made a side length sequence consecutively, then that sequence would just be arithmetic.
You can see to go from this square to this square, the side length you would have to multiply by 3. But then to go for the areas, you would have to multiply by 9.
By 9. So that's just square of that.
Yeah.
So does everybody understand?
Okay. Yeah, if a square had a side length that was 4 times this square, then the area would have to be 16 times this square. And this applies to any shape in general, any 2D shape. Like for example, the triangles, it's the same thing. This, if you go from side lengths, it would have to be just times the scale factor. But if you go by the area, it would have to be times the scale factor squared.
All right, so I think we should just move on.
Yeah.
If there's any other.
Okay, we're gonna move on. Okay, this last example is kind of important and a little tricky. So in this question, line segment AB is parallel to line segment EC. Name the two triangles that are similar in the image below, and also why are they similar? And for this question, try to remember what we worked on last week about the parallel lines and which angles are congruent. Because in order to see if a triangle is similar, all of their angles have to be equal to each other. So try to like mark which angles are equal. I mean, you can't really do that, but you could draw the picture.
And also when you write down the triangles which are similar, make sure that you have the correct order so that that order like corresponds.
Yeah, make sure you're writing the letters in the correct order.
Amy, I'll probably call on someone to explain.
Okay. You can call on someone.
All right. I'll call on someone who answered. All right. So Shalok. Oh, no, not Shalok. Well, yeah, Shalok. Shalok. How did you get your answer?
And if you just eyeballed it and said that they were similar, you could just tell us that.
Shalok, do you have a mic? I guess you're just not gonna answer. I'll type in chat. All right. Also, while Shulok is typing in chat, well, because I saw that the triangle was doubled.
They're actually not perfectly doubled.
Yeah, they're definitely not perfectly doubled. Let me call on someone else. Shri Ram, how did you get your answer?
And Shulk said that the angles are the same. How do you know the angles are the same?
Can you also tell me the angles are the same?
It's obvious that angle D is the same because it's the same as itself. But then how do you know like this angle E, and angle A are the same?
Wait, Amy, so in previous classes, did you guys cover like transversals and stuff?
Yes, we did.
Because I was just making sure.
Yeah, we did last time. Yep, they are. These two lines are parallel, and it's okay if you don't remember the name for this. And we told you we did tell you you didn't have to remember the name for this. But these angles are actually corresponding angles, and in a transversal, corresponding angles are congruent or equal. So that would mean that angle A and angle E are the same.
Angle B and angle C are the same, and since we know that all three angles of both triangles A, B, D, and ECD are the same, and both triangles are similar.
Yeah, so because they're yeah. This is pretty important. Once you know this, you could just eyeball it. If you know these two angles are the same, then this triangle and this triangle are always going to be the same once you know it.
You should never really like completely eyeball it. Just make sure that you know.
Yeah, but once you've gotten used to looking at triangles with parallel lines and transversals, then you can start eyeballing it. And we're going to show more examples on the next slide. So here are some more triangles that are going to be similar. So in this transversal, these two blue triangles would be similar. This angle would correspond to this angle. In other words, this angle and this angle are equal. And this angle and this angle are equal. And in this in these transversals, this large pink triangle and this smaller triangle would also be similar, with this angle is equal to this angle, and this angle is equal to that angle. And finally, for this last one, this large purple triangle and this smaller triangle are also similar, with this angle is corresponding to this angle. And these problems come up a lot in math counts because transversals there's a lot of different angle relationships between transversals. And we did talk about this last week, that you can show that these triangles are similar because you can see here that this angle is corresponding to this angle. This angle is the same as itself. So yeah, just whenever you see something like this, just remember that there are going to be similar triangles somewhere in the diagram. And now we have run out of time to do a Jamboard, but maybe we can do one question. So, okay. We might not. We may be able to get one question in. Okay, this is the first problem. You can just use a sticky note to put your answer on the slide. We did a similar problem during the lesson, so.
Amy, what problem are we asking them to solve?
I
think we should do 4,
what?
slide 4.
Oh, slide 4?
Yeah, let's make them do slide 4.
Okay.
And I don't think there's enough time to do a similarity problem. Yeah.
All right, okay, just do slide 4 and put your answer on slide 4. And, yeah.
It's okay, yeah, just do slide 6.
If you really have something, you can definitely go. Just try to see if you can like put quick answer on this slide.
Yep, they are.
If you have to go, you can go.
Also, just put like the proportion, the scale, if you want to. It's optional. The problem doesn't make you, but like. All right, so I think wait, isn't the perimeter 15 to 34? Yeah, I mean, what? Sorry, perimeter 15 to 24. The perimeter is actually 15. So the perimeter is actually 15 to 33 from my calculations.
Yeah.
So it's 15 to 33, and since the ratio is, so some people are saying that the triangles are similar. So the answer is actually no. Oh, did I say yes? Okay, that's my bad. So the answer is actually no, because 3 is the corresponding side to 9 in this situation, and they have a proportion of 3, a scale of 3. But then 7 and 14 have a proportion of 2, and 5 and 10 have a proportion of 2 as well. Therefore, the triangles aren't similar. So even if you added up the perimeters, they wouldn't follow the proportion either.
Yeah. Because
so I might have said yes. I thought that was a 6 or something. I don't know why I said yes, but the answer is definitely no.
Yeah, because when you go from this side to this side, you have to multiply by 3. But if you go to this side to this side, you multiply by 2. So because the scale factor isn't the same for all the sides, that means the triangles aren't similar.
All right. So I think class is over.
Yeah,
So thanks for attending today's class. I think the quiz will be up like shortly. Also, the recording will also be up on Google Classroom. So, are there feedback forms, Epsilon? Amy?
Yeah, I think Ashani posted it in the stream.
Be sure to fill out the feedback forms. If you have any questions, just post it
yeah,
on the stream or something, or
and stream
email
has
either.
the question too.
Yeah, sorry. So the theorem, wait. So why does the theorem work with 3D shapes? All right. I don't really think we got into that, and I don't really. I mean,
We probably shouldn't get into that right now, but you
yeah,
can
we're
just think.
probably not gonna get into that.
Yeah, but if you really want to know, you could stay after, and we can like explain it if you'd like.
Laws in math kind of carry over. They're all
Yeah.
all interconnected, so it's just something. But if you guys want to leave, yeah, thank you for attending today's class. We appreciate it. So those of you who stayed over, I'm assuming you either want to hear the explanation, or if you guys have it, or you guys have like a specific question you want to ask us, so you can like ask that right now. Does anybody have a question? Because I noticed that there's 3 people left, or 2 people left. So do you have a question? Oh, the person who asked the question's gone, Amy.
Oh, that's okay then.
Okay, so Gary and Kavya, do you guys have any questions, or are you guys just like here, staying here?